Welcome everyone to the lecture that we're going to have today on linked lists. We're going to cover some theory. We're going to talk about differences between linked lists and arrays and discuss the complexity of various algorithms involving them. Please feel free to take notes, to take photos, to record me. We're actually recording this so that you can watch it later as well. The video will be available on the webpage. So let's talk about why we might want to use linked lists. And to do that, I want you guys to imagine that you work at Uber. How many of you have heard of Uber before? Good. Everyone? Anyone not heard of Uber? Good. So you've probably experienced this either driving yourself, or if you have been in an Uber, that you provide your address, the Uber driver, or rather your starting address, where you want to end up. It creates a list of directions, and then those directions are typically displayed to the driver. They start to follow them and take you to your destination. Okay, so in general, we have these lists of directions. They are ordered. And the way we're going to model Uber today is we are at some point in these lists of directions, or a list of directions. Let's imagine that we don't just have one driver and one user, one client, but we're now doing Uber Pool. And if you haven't used Uber Pool, that allows you to ride share with other people through the Uber app. So now, in the middle of driving, the driver may get a new set of directions. So wherever we are, we're going to insert some new directions to pick up another customer, maybe to drop someone else off. We're going to say that the new directions will follow immediately after the current step where we are in this list. So we're often adding directions to the middle of this list. On occasion, the customer will cancel. So whatever list I have, I need to remove a set of directions that I've added. I'm not going to worry about searching the list, so I could, but this is not my primary concern today. I need to also store the completed trips for accounting purposes. So if you've heard of a queue before, this is not going to be a queue. We're not going to pop things off. We want to store the whole list. And the idea here is that I have millions of users. And so I want to make this fast, even though the lists aren't very long. I want to make this addition and deletion, these modifications to the list, very quick. Otherwise, my performance will suffer and people will go use Lyft. So let's use a primitive array for storing the list of directions. And it might look something like this, conceptually. Starting at index 1, up to some size. Each of these would be a direction. How big should my default array be? What do you guys think? Any suggestions?
50.
50? That's aggressive, but not entirely off. So it turns out if I wanted to drive from George Mason University to Stanford, that's somewhere on the order of 50 steps. So 50 maybe is the max size, or the largest reasonable thing you might want to do. So if I use 50 and I have a really long trip, I can record all of it. But what if most of my trips are shorter? Do you think they're shorter than 50 typically? Do you take 50 steps when you drive somewhere? What's more common?
20.
20, 10, something like that.
Yeah.
So maybe I'll make this a little bit smaller, because if I'm always using 50, that wastes a lot of space. So let's say that my default size is 10. Every time someone asks Uber to take them from one place to another, it will start with an array of size 10 and stick the directions in there. And so I'll just draw little squiggle lines for actual directions. These may or may not be completely used up. If I have a really long trip, I need something longer than this. And so I can't draw it here, but I would add to the bottom. These are not dynamic arrays though, and so I might realize if it's too long, I need to maybe create a separate array and make sure I can fit everything in there. Okay, that's not too bad. But the issue here, if I'm limiting myself to size 10, is if suddenly I add a new set of directions, and maybe those directions also are on the order of magnitude of 10. And so if I need to expand this list, maybe I'll double it to have 20 spaces, I need to copy everything over from my original list and then add in the new stuff, N for new, after that in the middle somewhere, and then continue to copy if there's something after that as well. Do you guys think that's efficient? Does that seem like a good idea? No, it was very boring to watch me do this on the board, right? I have the same problem if I need to now remove something from this larger array, maybe to make it a smaller, or just remove in general. Even within the small array, if I want to get rid of one direction, I then need to shift everything up, also in the larger array. And that's the same sort of copying that's pretty inefficient. So, leading question, are primitive arrays a good implementation for this? What do you think?
No.
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 Very good. Let's take a pause and just talk about complexity here with some amount of formality. A reminder as to what big O complexity is, assuming that you've heard it before. Here we're trying to measure the number of computations we perform for some input of size n. So n is not a fixed number, and n is some number. We can measure computations, we can measure comparisons, assignments, that's up to us. And what we want to do is look at the worst case scenario in terms of n. How many comparisons do we have to do as n grows? In this analysis, we throw away constants and other terms that are insignificant as n grows. And as an example, imagine this is a list of strings. Somewhere in here, I'm looking for a particular word, let's say the word cat. I'm going to start at the beginning and see if each of these cells is cat or not. This is called a linear search. Anybody want to tell me what the complexity is? If the list is of size n, what is the worst case in terms of the number of cells we have to visit to find cat, or to see if it's there or not?
Well, it's all of them.
Yeah, all of them, right? Yes. So you will have to visit n, and so linear search, we say, has a complexity big O of n. So if we go back to our array here, in terms of what we were deciding to do earlier, when we need to add new directions to our list of Uber directions, the worst case scenario is we have to copy over n directions into a new array and then add the new ones at the end. It's not very efficient. The same problem if we delete something. If we need to delete a direction at the very beginning, we can delete that, but then we have to shift up and copy all n minus 1 to do that. So that's on the order of n. That can take time if these arrays are long. Ours are not, but we have so many of them going on simultaneously, we're going to argue that efficiency is important. It is slow to keep copying over the array contents every time we want to add something or remove something. And you might say, hey, Joe had a great suggestion, let's make the arrays really large, of size 50, and then most of the time we won't have to worry about this, but then we are potentially wasting a lot of space. And so we want to see if we can do something better. Sure we can, at least for this example. How? Linked lists. So a linked list, you can see on the slide, is something that is made up of nodes. Nodes will store data, that can be conceptually anything. In our case, it'll be a set of directions. And a linked list node will also store a pointer to the next node in the list. We need a way to point to the head of the list, and so we have a head pointer. The last node in the list will point to null. It will not go anywhere. And we oftentimes also have a tail pointer for reasons that we'll see later. I'm going to assert that linked lists are better than arrays at insertion and deletion when we don't need to copy over big chunks of the array to accommodate a larger or smaller size, and when we avoid shifting elements to insert or delete. Linked lists also can save space if our arrays are very sparsely populated. So if for Uber we had an array of size 50 or 100 and we only usually used 5 or 10, even though linked lists need an extra piece of memory to store the next pointers or the next links, that could still be more efficient than having an oversized array. This slide here shows various trade-offs in terms of runtime between linked lists and fixed size arrays. I don't expect you to memorize this necessarily. I'd like you for the exam to understand all of them and be able to derive them. If there's anything on this slide that doesn't make sense, please feel free to message me on Piazza and I'll be happy to go into more detail or come to office hours, etc. So if you look at the values here, they're actually very similar to arrays in terms of searching, deletion, some of these insertions. Linked lists are not necessarily all that efficient, but they do form the foundation for other data structures that are very useful and we'll learn about in this class, such as binary search trees. That'll be in the next lecture. So let's go through some linked list algorithms. And I'm going to do this in pseudocode because I want us to plan how we're going to code up these algorithms in a little bit. We're going to code them up later in Java or C++, but for now, just pseudocode here on the board. Talk about how to create a linked list. Let's then add to the end of that linked list, searching for the end from the beginning, and just searching through a linked list, maybe to delete an element. Okay. Starting with linked list creation, let's define a node type. Again, I'm doing pseudocode on the board. If you want to follow along and get a head start, feel free to code this up in Java. That's what the first set of exercises are in. So what did I say earlier that we wanted to store? I said two things. Can anyone name one of the things we want to store in this node in the linked list?
The direction.
Yeah, so we draw a little diagram. So if you remember the diagram from earlier, we want to store a pointer to the next node. So that will also be of the node type. Next. And then for my example here, perhaps we'll store the driving direction. And that's enough for now. Let's now create a linked list. How would we do that? Well, we want to create the head. So having this definition, maybe in another file that would use the definition, we create a node. And we want to set what we're storing, which for our example is the driving direction, equal to some element. And let's say this element will store the direction. I'm not writing it all out to save space. And maybe in how many feet we'll make that turn. I set the driving direction, and since my linked list here only has size of 1, the next node from the head will just be null. Questions? Pretty easy? Okay. Let's add another node to the head. So I'll just draw that up here. How do I create a node? Did I already create a node here? Do you guys know how to do that? Just presumably call some constructor. Node, new node, node. Let's set its driving direction. I'm not going to fill it out, but some direction, some number of feet. Set its next equal to null. And any ideas how to connect the head to this new node?
The head's next.
Very good.
Is the new node.
Make sense? Good. Let me just sort of... Does anybody want to see this in memory? Having me draw out memory? Or you guys got it? It's simple enough? Okay. Good. If you want to look up the same pseudocode in more detail, here it is on the slide, but we did the same thing on the board. So let's try now to write a method or a function, in this case a function, to insert something at the end. I'm going to erase all this. But keep in mind that node class. And so we're going to fill this out, the function to add a node, given the head of a list, and the new data that we want to store. Before we start writing code, let's think about some test cases first. We're just going to assume, just for this example, that the linked list will never be empty. So head will never be null. That's a choice we're making now, and the exercises, I think it's a little different, but we're going to run with it here. What are some interesting test cases here? Well, a linked list of size 1, which would look like this. How do we add something to that? Well, you go to the end and you would put the new node there. Let's also make sure that we can handle a linked list with more than one element in it. So making sure that we can get to the end of it. Looking at these examples and thinking about it, how would I start this? I need to go from the beginning and follow these next pointers until I reach the end, and then I would insert my new node at the end. If we don't have this view of memory and we just have the head pointer, do we know at the beginning how many nodes there are in that list if we just have a head pointer? We don't, right? So we have to go through and follow the next pointers. Any suggestions of what we would use to do that? What programming construct might be helpful here? Something simple. Well, decision statements, looping. How about a while loop? Can we use a while loop to go through while there are new nodes to visit them, and then go forward? Let's try that. So as a hint, we'll use a while loop. To iterate over a list like this, you want to start something at the beginning. I'm going to call it the current node, and I'm going to set it equal to the head. While the next node is not null, move it forward. So initially current is equal to the head. Is the next one of current null? No. So I move current forward here. Is the next one of current null, or was it originally? Yes, so I leave it there, which is what I want to have happen. Once I'm here, I know where to place the new node, so I can create it like before. Set up its driving direction. Make sure that its next points to null. And then current, not current, but current.next, I set equal to my new node. So current is at the end, set it equal to the new node. And I've added a new node to the end. Questions? Okay. Question for you. Would that work? I don't know. Let's try it out. Originally, the current is equal to the head. While current is not null, go to current.next, so it goes here.
Will the last one be a null pointer exception?
Yeah, let's
Some
see it.
sort?
So pretend this one has the full 3.
Your language has those?
Mm-hmm. This one goes forward here. Cur is still not null, so cur goes to current.next, which means cur points to null right here. Okay, all this is fine, but at that point current is null, so you can't do current.next and you get a null pointer exception. And so I'm just showing the solutions on the slide. That's a common mistake, but easy enough to see and then rectify. Questions? Pretty straightforward. Let's try searching a linked list now. So I will leave some of this up because we're going to recycle it. We're going to return the node that we found. And in this function, pass in the head. And I'll just call it the target to be a little clearer. Some test cases to think about here. List of different sizes. I'm also interested in trying to find something that's at the beginning. That's a good test case. Finding something that's at the very end. That's another test case. And then finding something in the middle. So let's try to keep that in mind, see if it matters or not. Okay, once again, we're going to use the same model here of setting a current equal to the head and then going through and seeing if, well, the node that we're looking at I'll just leave this as is. If the node that we're looking at equals the target, conceptually, then let's return the current element. And if we didn't hit this return statement, then like before, just move it forward, erase this. If we never hit that return statement, then perhaps I will return null if I don't find the element in the list. That was probably a good test case that I should have thought about earlier. Okay, let's see sort of conceptually will this work. So if it's at the beginning, we find it because current is immediately in the right place. Its next is not null. It matches returns current. In the middle here, so we would go forward 1. Current is now here. Its next is not null. It matches the target, return it. How about if our data is at the end? So we would visit here, we'd visit here. Still haven't found it. Current equals current.next. While current.next does not equal null. Does current.next equal null here? It does. That means I pop out of that while loop and I return null, and yet my element was there. That's a bug, right? How can I fix it? Let it go to the end. So here, when it's here, it would come in and that would return cur there. If the element was never in here, then current would get to null, at which point I would leave and return null because I couldn't find it. Questions?